Alright, hello everyone. In this video we are going to be going over molecular and electron geometry, as well as going over the bonding angles. So this is a lot about basically just the molecular geometry. We're going to also get a little bit into the bonding angles as mentioned. So just to start off, let's talk about the difference between molecular geometry and electron geometry, because they are different, and I actually didn't even know that until this year. I never even learned that electron geometry was a thing, so it's a pretty cool thing to learn here. So with molecular geometry, you're treating the lone pairs as electrons. So what electrons do, what do lone pair electrons do? The lone pair electrons are very negatively charged, so they actually end up pushing the other elements. So if we were to draw something like dihydrogen monoxide or good old water, looks like this, H2O, your first thought is to draw it like this before you add on those lone pair electrons, of course. Once you go about doing your, your Lewis structure and you find out that there's two bonds there, what's going to happen is that these are very negatively charged, so it's going to be like, get these other negatively charged things away from me. They're also very large, so they take up like a little bit more space usually, these lone pairs, because again, like, they're so negatively charged that they have to have like this big radius around them that's like, don't touch me, and this is this guy, don't touch me. So these guys are getting real close to the don't touch me zone, so what they're going to have to do is they're going to have to move down. So that's why there is a difference between molecular geometry and electron geometry, is because once you have those lone pairs, they're going to push the other elements in the molecule. This is all because of VSEPR theory, which is valence shell electron pair repulsion, which basically just means that if you have a lone pair of electrons, or two, they're going to push them. But any amount of lone pair electrons is going to cause that to happen, right? So again, lone pairs are very negatively charged. They have this big bubble around them that's basically like, don't come near this bubble, because again, it's like a magnet, right? So let's say that this is negatively charged and this is negatively charged. What they're going to do is they're going to repel each other. So these guys are going to have to move down this way, because they're like, oh crap, I'm near something that's negative, not cool. Let's get away from that whole situation. So that's why it becomes bent. And then with electron geometry, you're treating the lone pairs as if they're atoms. So basically what you do is, let's say again that we have, let's take a look at this one, right? These are just going to be treated like regular old atoms, right? So that's pretty much, or you're treating them as, treat the lone pairs as, treat the lone pairs as atoms. So what I always actually do in my head is that I just draw it out like this. I write A so that I know it's an atom, then I do the rest of it, and then I'm like, okay, well, if it's 4, then what's that gonna be, right? So I'm just treating these like other atoms in the molecule versus treating them as electrons. So in this situation, it would actually end up looking like this, which if you twist your head a little bit, you kind of get the same thing, but they're no longer pushing these guys, right? So this is, the molecular geometry is when you're treating them as electrons, so they're going to be pushing if there is any lone pairs. And then with electron geometry, you're treating them as atoms, so there's going to be no pushing. So you're just treating them as regular old atoms. So let's go through how we're going to do that. Where am I going? I'm going here. Alright, so how to determine the molecular geometry. So the first thing you're going to do is draw your Lewis structure, and I have a little note here is to be careful of those non-bonding electrons or lone pairs, also known as lone pair electrons. Because again, if you have those lone pairs, it's going to change some things, right, with the molecular geometry. So you're going to draw the Lewis structure, be careful of the non-bonding electrons, then you're going to determine the geometry using VSEPR theory. So when I say that, I'll go through like a chart, but for me, I just like to think about it like hypothetically, right? So let's say we have an atom that looks like this. It's got 2 lone pairs on it, and then it has some other atom and some other atom and some other atom. These guys are going to push these guys down, so it's going to end up looking something like this. Atom, atom, atom. And when you think of this in a 3D space, I I don't know, I don't remember what the website was, but if you think of this in a 3D space, it's going to actually look like a pyramid, right? So it's going to be like one of them is going behind, one of them's going to be here, one of them's going to be here, and this is like the top is your A. This is going behind, so maybe I can make this look a little bit better for you guys, so it looks like it's going behind. You really have to think in like a 3D sense here. This is like something that I had to develop as I like went through college, but let's say that's going behind, right? So if you can visualize that, that's going behind, this is coming at you. Make it maybe like larger towards the bottom. So that's coming at you, and that's going behind. That's what it would look like, right? Kind of looks like a pyramid. So that's how I think of it when I say using Vesper theory, because that's pushing it, it's going to look down, and then that's going to be like that. So for me, I know that that's going to be trigonal pyramidal, because it looks like a pyramid, and there's 3 things coming off that central atom. But that's my way of doing it when I see that. Or you could either memorize a chart or just write it down on your note sheet, whatever you want to do. Whatever works best for you. Then you want to match the known bonding angles or think critically. So again, another thing where you can either choose to think critically or just write these down or just memorize them, whatever you want to do. For me, I kind of like to do both, so that's why I say and. So here I'm going to think, right? So I know that personally, something that is trigonal is likely going to have 120 degrees, but since it's getting pushed so much, I think it's going to be different, and here it even says that it's going to be different, so it's going to be a little bit less than 120, and then I'm just going to check it over here, and I'm like, okay, trigonal pyramidal is 107, cool, so that'll be the bond angle that I use for this example. But let's go through those known angles. So linear is going to be 180, so we can just think like carbon dioxide, that's linear. A circle is 360. If you divide that by 2, this is going to be 180. It's kind of like going back to geometry in high school. So hopefully you remember that anything linear is 180 from high school. And then linear bent is going to look something like this. Good old example here. That's going to be 109.5 degrees. Trigonal pyramidal, we just went over, that's going to be 107. Trigonal planar, again, it's going to be a similar situation where we have to think about this in a 3D sense. Let's say this is like F, and F. These are going to be 120 degrees, so that's trigonal planar, and then tetrahedral is going to be something like this. H, 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 and H. And these are going to be 109.5. Again, you have to think about this in like a 3D sense. You might be looking at this and you're like, oh, why is that not 95? That's because in a 3D world, they're actually able to spread out a bit more because they have like a whole nother axis they can go to. So they can spread out a little bit further apart from each other, giving them that 109.5. All right, so let's go through that geometry chart. So maybe this will help a little bit. Counting the number of atoms attached to the central will help a little bit, right? It'll help at least with naming, right? So let's take a look at linear. Linear and bent is either going to be 1 or 2 attached to the center. It's highly unlikely that you're going to get any more than that with linear. It's possible that you have something like C, but at the same time, he'd have to ask us according to which part of it, right? So, an example of linear, I said AA, but let's give you guys an example. Let me think of one. Just hydrogen as a gaseous molecule, that's linear, or carbon dioxide, those are both linear, right? So if it's 1 or 2, so it's going to be 1 or 2 attached to the center. And now let's look at bent is going to be 2. So bent only occurs if it's linear with lone pairs, right? So if it's something that can be linear, so let's see, H2O is our example again. So it could have been linear if it was like this, But as you remember, there's those lone pairs that are going to bend these hydrogens down. So it's going to actually look like this. There's 2 lone pairs, right? So again, one or two is always going to be linear or bent. If it has 3, it's going to be either trigonal pyramidal or trigonal planar. If it's 3 atoms attached to it with no lone pair electrons, it's just going to be trigonal planar, right? Nothing's going to be bending. It's going to just stay in a plane, and it's going to be chilling there, right? And then with trigonal pyramidal, because there's that lone pair of electrons, what's going to happen is that those 3 atoms attached to the central is going to be bent, right? And the only way that it can bend is a way in which it looks like a pyramid, and that's why we call it trigonal pyramidal. And then tetrahedral, pretty simple. There's not really going to be much of a exhaustive list of things to where there could be lone pairs attached to something that's tetrahedral, so that's kind of why we ended there. I mean, if there was a situation with that, that would go with the group, like anything below group 3, but Professor Sherlock said that he's only going to be testing us on the geometries of things that are above that group 3. So we're not dealing with a D block, and the reason why the highest that we can get is tetrahedral is because if you look at it like this, we have 8. If we add these up, right, we're going to have 8. So we have 2, 4, 6, 8 valence shell electrons on this central atom, and we know that 8 is that magic number, so we can't get more than that unless there's a D group. So with that being said, tetrahedral is the only one that we're going to see when there's 4 atoms attached to that central atom. So just to review, linear is going to be straight, no lone pair electrons for something that has 1 or 2 atoms attached to that central atom. For bent, it's going to be 2 with the addition of 1 or 2 lone pair electrons on that central atom. And then trigonal pyramidal is going to be something that has 3 things attached to the central atom with the lone pair electrons bending them, so that's why it's pyramidal and not planar. And then planar is just that same situation where you have 3 of them. And there's no lone pair electrons. And then finally, tetrahedral is going to be when you have 4 and there's no lone pairs. Again, you can always memorize this chart, or you can just think about it critically if you're able to do that. And if you can't do either of those, you have that note sheet. You can always write it down. That's always a safe bet. Okay, so let's go through some examples. Is this an example problem? Yeah, geometry examples. So I'm telling you and myself to do the electron geometry, the molecular geometry, and the bonding angles. So first thing that we're going to do is we're going to draw it out. So we're going to have nitrogen. Actually, I'm going to do this. I have nitrogen, and we're going to have hydrogen, hydrogen, and hydrogen. Once you go through and you do all of your numbers and everything, you're going to find out that nitrogen has 5. And then we have 5 plus 3. It's going to be 8. Here we have 6. And then what we're going to do is we're going to add on a lone pair there, right? So right now, when I'm looking at this, the molecular geometry, I want to say, is going to be pyramidal, because we have 3, trigonal pyramidal, because we have 3, so it's going to be trigonal. And because we have that lone pair there, it's going to be pyramidal. So I'm going to say trigonal pyramidal. Awesome. So now let's look at the electron geometry. So let's treat this as if it's an atom. What does that look like? That looks like tetrahedral to me because there's 3 atoms attached. So we're going to say tetrahedral. Now let's determine the bond angle. So I'm going to do the bond angle of the, I'm like, why is it not deleting the thing I want? So I'm going to actually do the bond angle of the molecular geometry. I'm assuming that we're going to be asked which bond angle, but because in nature you're really looking at the molecular geometry, not the electron geometry, we are going to just look at the bond angle for the molecular geometry. But that, again, like, you'll be asked, and if he doesn't say specifically on the test, definitely go up and ask and be like, all right, do you want the bond angle of molecular or electron? Okay, so trigonal pyramidal. So I know that tetrahedral, well, no, let's take a look at tetrahedral, right? So if we look and treat this as if it was the electron geometry, this would be 109.5. But as we learned before, this is very big and it's very electron dense, I guess we could say. It has a lot of electrons, so this big thing is like, all right, get away from me, please leave. And we know that that other number that we have to memorize for pyramidal is 107. So this is going to be 107 because if we were to treat it like it was tetrahedral, it would be 109. But since we're going to look at the molecular geometry and do the bond angle of that, we're going to treat this as if it is the lone pair of electrons, and we're going to say, all right, well, we're pushing this down. So what's the number that's going to be a little bit less than 109.5? And that'll be 107. Again, this kind of does come down to like memorization, but it's memorization and thinking critically, or you could just write it down on your note sheet and you don't have to do either of those things. But yeah. All right, so let's take a look at the next one. We have CH2O. So carbon's going to be our central. I'm going to do 2 hydrogens here, do an oxygen there. So let's do the molecular geometry, electron geometry, and the bond angle. Okay, so molecular geometry. Since this thing has 1, 2, 3 on it and no lone pairs attached to the central atom, we're going to say that it is trigonal planar. Trigonal planar. And because there are no lone pair electrons on the central atom, the molecular geometry and the electron geometry is going to be the same, so it's going to be trigonal planar. All right, and now the bond angle of something that is trigonal planar, let's think. So trigonal planar, since it's planar, we can think of it as like a circle, a flat circle, and if we cut a circle into 3 parts, each part is going to be 120, so 360 divided by 3. I forget how to, guys, I literally forget how to do math this way, but I'm pretty sure if we do it like that, it's going to be 120, but I just do it on my calculator, and I highly suggest you do it on your calculator as well. So it's going to be 120. Wow, I have not seen, like, long division, that's what it's called. I haven't seen that in ages. Alright, so that is it for all the practice, or the examples. So I do highly encourage you guys to take a second and try to look through these practice problems, and we'll go through them in just a second. Alright, so let's start off with a fairly easy one. So let's draw the Lewis structure first. So we have 2 hydrogens and oxygen is going to be the center, and the reason why oxygen is going to be in the center, as we know from our Lewis structure, is because hydrogen can't be the center because hydrogen can only have 1 bond. So it's going to look like this, and then again, once we do our numbers, we're going to say hydrogen is 2 plus 6, 2 plus 6 is 8, we have 1, 2, 3, 4, 5, 6, 7, 8. Cool, that's going to be our structure. So let's do the molecular geometry, the electron geometry, and the bond angle. Okay, so the molecular geometry is going to be linear bent. The reason why I know that is because it is linear because it has something that it has 2 attached to the center. So I know it's going to be something that's linear, right? Because it's 1 or 2 for anything that's linear. And then I know it's going to be bent because it has those lone pairs. So now let's take a look at the electron geometry. So we're going to do the same thing that I did before, where I'm just going to act like we have, oh, I got something in my eye. Sorry. Just like twitched out a little. So we're going to pretend that those electrons are now atoms, and what we're going to do is we are going to say, well, what does this look like? This to me looks like it is going to be tetrahedral. Tetrahedral. I always have to think about it because I'm like, tetra. I'm like, what means 4? But 4 is tetrahedral. And yeah, so that will be the answer there. And then our bond angle, again, we're going to use the molecular geometry, but these two are actually the same, and it's going to be 109.5 degrees. And reason being is because that's just the geometry of something that's bent, I guess. But you could think about it critically and think, okay, so it's gonna be less than 180, but it's a lot less than 180. So it's not gonna be 120, but it's, yeah. So that's just like one that you kind of have to memorize because there's not much of a way to think about it critically. But yeah, you could also think about it like this, like they're so strong that they kind of are almost the same as having two atoms there. So it's like really pushing it. So it's gonna be the same as tetrahedral. However you want to think of it. Personally, I just kind of have that memorized, that anything that's linear bent is 109.5. Okay, so let's move on to barium chloride. Barium chloride, that's not what that is. Ignore that I said that, please, because that's embarrassing. That would be boron trichloride? Something like that. So first we're going to draw that out again. We're just going to draw it and we're going to do our addition really quickly. So let's do, this has 7, so 7 times 3 is 21 plus 3 is 24. So we have 24 to get to. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Cool, we don't have to do anything else to it. So the molecular geometry and the electron geometry is going to be the same because there's no lone pairs on that central atom. So the molecular geometry here, since there's 3 things with no lone pairs, is going to be trigonal planar. I'm just going to write trigonal plane because I don't have enough room. And I'm just going to write quote down here because these will be the same. And the bond angle of trigonal planar is 120 degrees. Again, because it's planar, you can just divide 360 by 3, and there's your answer. All right, let's look at this next one. We have C2H2. So our carbons are going to be our central. H is going to be on the outside. And let's do our numbers here. So we have C is 4, so 8 plus 2 is 10. 1, 2, 3, 4, 5, 6. So that means that we have 4 left over. And what I'm going to do is I'm going to put them here. And these are going to have resonance and they're going to turn into triple bonds. So I'm just like quickly going through these. I like highly, I don't think that anybody should at this level be doing it as fast as like I am. The only reason why I'm able to do it so fast is because I've taken orgo and I have basically all of these molecular geometries and everything memorized just from dealing with them so much in their lowest structure. So if you can do them that fast, and that's really impressive, but if you're taking some more time to do the lowest structure, like that's totally fine. Like don't be worried. Just figured I'd let you know that. Okay, so let's take a look at our molecular geometry, our electron geometry, and our bonding angle. Okay, so the molecular geometry here, there's no lone pairs on either of the central atoms, so we're going to say linear. And the electron geometry is going to be the same. Just going to check, because I think we did this one in class. Okay. So yeah, that one's going to be linear, and then the bond angle, because it's linear, is going to be 180 degrees. Last one until we're done. Let's do carbon in the center. We're going to do our oxygens on the side. Again, we're going to do the same thing where we're doing 6 times 2 is 12 plus 4 is 16. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 12, 13, 14, 15, 16. These are going to have negative formal charges, and carbon isn't happy, so it's going to end up looking like this. Oops. Be sure to put those there. So our molecular geometry, because this is something that has 2 on the center, that means that it's either going to be linear or bent. And because, sorry, I'm I dozed off for a second. So it's either going to be linear or bent because it has 2 on the outside of the center. So it's going to be linear because there's no lone pairs on the center, and it's going to be the same here. And then the bonding angle is going to be 180. I just want to go back to this one. You might be confused now that we've gone over like these ones. You might be like, well, which one's the center? So you can pick either of them. You can just say that, like, okay, well, this one doesn't have anything else attached to it, so it's going to have 2 things attached to it. This one only has 2 things attached to it. Like, you can think of them like personally. Like, personally, this one only has 2 things attached to it. This one only has 2 things attached to it. This one itself has 3. This one itself has 4. This one has 2. So you're just looking at each individual atom to figure out which one it is. So that's why that one will also be linear. But yeah, so I hope that this helps. It was kind of a long video, but there's a lot to go over in this little section. So I hope that this helps, and thank you all for watching.